Welcome back. In this set, we study the algebra of events, which is based on set theory. We then apply it to the axiomatic definition of probability theory and derive our first results on probability theory. Finally, we address probability problems in which all outcomes are equally likely. So let's get going. What is important to remember is that events are simply sets, and as such, they are unordered collections of discrete elements, and we denote them with curly braces, as you see. And we just have to remember that this collection of elements are unordered, and it doesn't matter the order in which we write them or how many times we repeat any of the elements. The other nomenclature that is important for us is the empty set, which is denoted by the Greek letter phi, or the empty curly braces. There are going to be a few standard numerical sets. One of the important such sets is the set of natural numbers, which we can start from 0 or n, or 1, and depends on the example that we discuss. Another important numerical set is the set of integers, negative and non-negative integers. The set of positive integers, which is denoted with z plus, as you see in the slide. And you can view them also as counting numbers, or set of natural numbers, when we assume that the first counting number is 1. The set of real numbers is also important, is any decimal number of arbitrary precision, as you see. The set of rational numbers is the set of all fractions, and of course we require that in a fraction a divided by b, the a and b are two integers, and b has to be non-zero. The irrational numbers are numbers that are real numbers, but they cannot be described as fractions. A well-known example is pi, and it's a real number, but it's not a fraction. More important notation is how we denote when an element is in a set and when a set is a member of another set. So we do epsilon to denote the case in which we have an element belonging to a set. And for example, 3 is an element of a set. We denote by 3 epsilon s. And when we say we want to denote that an element is not in a set, is just using the epsilon with negation. When we denote when a set is a subset of another set, a set is part of another set by the subset notation, which is denoted that way. And we say that a set is a subset of another set if and only if every element of the subset S is an element of the larger set T. And we denote that with S subset of T that way. When we use the notation of proper subset, that means that S is a subset of T in this case, but S is not equal to T, cannot be equal to T. So there are more elements in T than there are in S. Cardinality of sets is also important for our discussion of events. By definition, the set is said to be finite if its cardinality, or the number of elements in the set, is a non-negative finite integer. Otherwise, we say that it is an infinite set. And for example, the set of numbers that we discussed before, starting from the set of natural numbers all the way to the set of irrational numbers, are each infinite. And of course, you remember that not all integers are the same. The smallest infinite number is the set of natural numbers. And as you recall, maybe the set of real numbers has an infinite number more of numbers than the set of natural numbers. Luckily for us, this won't impact our discussion of cardinality of sets, or i.e. the number of events in our sets. So we could denote sets by using the curly braces notation and explicitly state all the elements that we have in a particular set, but that would become cumbersome when we have very large sets. Or alternatively, we could do a descriptive statement of what the set is by talking about the characteristics of the elements in that set, such as the set of all natural numbers. It would be impossible for us to list all of them explicitly. For such purposes, when we want to give a descriptive statement of what a set is, we use what is called the set builder notation, which allows for a very concise definition of any type of set we want to discuss. And we essentially state in the set builder notation that every element of a set satisfies a particular proposition. And remember that a proposition is a statement that is true or false, but not both. So, for example, we have, if we want to talk about the set of even integers, we can do it by saying all the elements x, such that x is an even integer, or we have alternative ways to do the set builder notation, or use the set builder notation in this case. We can say the set of numbers 2 times x, where x is an integer. Both are these two and others are equivalent ways to specify the same set of elements, well, because all of those ways are equivalent statements of the characteristics that the elements of the set satisfy. Okay, so we have now gone over the nomenclature we use to discuss sets, which are going to be our ways to denote events. And the same way we do with sets, we want to combine events, we want to combine sets, we want to combine events. And for those purposes, we need to use set theoretic operations, which each set theoretic operation allows us to build new sets from smaller sets or some other different sets. So given two sets A and B, there are 4 important set builder operations that we list there: union, intersection, set difference, and complement. And we use the big U to denote the union. You can view it as an upside down U to denote the intersection. Set difference is the minus sign, and the complement is the bar on top of a set, or superscript C, as we will use in the future. So when we apply these operations to sets, we get new sets as a result. As you remember, we have truth tables in propositional logic. The equivalent for set theory is what is called set membership tables. I abbreviate them by SMT. And as I said, is analogous to truth tables. An SMT indicates the combinations of sets to which an element can belong. One in a set membership table is used to indicate that an element is in a set, just like a 1 indicates that a statement is true in a truth table. As here in the case that the element is not in a set, just like a truth table has a 0 to indicate that some statement is false. And we can list the membership table of each set operation, just like we do for logic operations, and we will see some examples next. To begin with, we look at the simplest set operation, which is the complement. And what you see here is we have a set A, and then we have its complement. And you see here that an element may not be in the set A or may be in set A, and we indicate that by 0 or 1 correspondingly. When an element X is not in set A, the definition of the complement is such that then element X is in the complement of set A. And vice versa, if an element is in set A, then by definition of the complement, the element is not in the complement of A. And to denote this very same information that we have in the set membership table of the complement operation, you see that to denote the complement of an event A or a set A, we can state that by the set of elements, which we indicate by the curly brackets, and we denote the element X such that, which is the vertical bar, X is not in set A. And this definition using set builder notation is the same as our set membership table. Moving on to more interesting operations, the intersection. You see here the rows of the set membership table now have all the possible combinations of membership in this case set A and set B. And we go from an element X not being in either A or B, all the way to a set element X being in A and B. And the definition of the intersection is that for an element X to be in the intersection of A and B, the element has to be in A and it has to be in B. That's why you see as a result in the set membership table that for the intersection of A with B, we have that an element does not belong to the intersection unless it is the case that it is in both sets A and B. Again, if we use the set builder notation, we can describe the very same information we have in the SMT for the intersection of two events or two sets by just saying the intersection of A with B is the set of elements X such that X is in A and X is in B. By the same token, when we talk about the union of two events, the definition of the union of two events is a set such that an element is in the union of A with B if the element is in A or the element is in B. As a result, you see that an element is not in the union of A with B only when the element is not in either A or B. And that's what you see in the SMT, that we have no membership for the union only for the case in which the element is X is not in A and is not in B. And again, if we look at the set set definition using the set builder notation, we can define the union of A with B as the set of elements X such that X is in A or X is in B. Notice that or is, it can be in A, it can be in B, or it can be in both. That's why you have membership for all those three cases. More interesting set operation is set difference, which is sort of similar to implication in propositional logic. What the definition for set difference is an element X is in the set difference of A with B. You can think of it as A minus B. If the element is in the first set A and the element is not in the second set B. That's why you have the 1 for membership in A minus B only for the case in which the element is in A but is not in B. And again, with set building notation, we denote the set as the set of all elements X such that X is in A and X is not in B. Now, you notice that we have this conjunction of these two statements, X in A and X not in B. So you see that we can represent the set difference of A minus B with the and the intersection of set A with the complement of B as the set of all elements such that X is in the first set A and X is not in set B. This is the first time, well, this is one good example of having two equivalent definitions of the same set using set differences. The set difference of A with B is equivalent to the intersection of A with the complement of B. Building up on this notion of equivalency, we can use set membership tables to determine whether or not two sets are the same or equivalent to each other, which in terms of the set membership table, it means that all the elements of one set are also elements of the second set. So in this example, we want to determine whether the set, the universal set U is equivalent to this complex definition of a set based on the intersection of A with the union of itself with another set B, all of that complemented and having a union with set B. Is all of this complicated description of a set equivalent to the universal set? And to answer the question, we can simply go down the list of all the possible input combinations for our set membership and decide on a column-by-column basis the membership of the various parts of the description of the complex set, and then compare that with the universal set. So what we have here is, you see, we are listing all the possible input combinations of membership for A and B, and then I list here the complement of A. Now, to look at the union of the complement of A with B, we then look at the union of these two sets. And of course, notice that we will have 1 for membership whenever we have an element being in B or in the complement of A. And that's what the result you see here. Similarly, for this intersection of A with this union, which I call for shorthand S, we take the intersection of A with the union of B with the complement of A, and we obtain this membership. And notice that the membership in this intersection happens only when the elements are in A and also in this union. And that's what you see, 1 for membership only in the last row. Then we complement that, and you see all 1s, and then except for the last row, which is the one that we have for S, that we have to have a 0 for the complement of S. And then we have this complement of S, and we have B. And if we do the union, then we have that for all possible combinations of membership, we have that there is always at least one element in the resulting set. Therefore, we can conclude that this complex description of a set is equivalent to the universal set.